Máté Farkas from ICFO Barcelona will talk about Bell non-locality is not sufficient for security of standardized independent quantum key distribution protocols. Great title. So Máté, please.
Yes, thank you. Thank you for the introduction. And thank you for the organizer for putting this event together, and the program committee for accepting my talk, whose title Zoltán just read. And this is a work in collaboration of ICFO Barcelona, the group of Tony Yasin, and the group of Janko Wodiński from Warsaw. And you can find it on the archive at this link. So I will start. Basically, I will just explain the two concepts that appear in the title mostly, and then briefly just tell you what results are. So I will start with Bell non-locality, which is good because it kind of sets the stage and the arena in which the key distribution protocol we'll be looking at. So we start with non-local scenarios, and these are scenarios that consist of two parties that are usually labeled as Alice and Bob. And we can just think of this as like some two distant laboratories where Alice has access to some sort of device which has some buttons that we say are the settings. And then whenever you press a button, which is labeled by this X, you get some kind of answer, which is labeled by A. And these are like some just discrete numbers, some integers. So you can imagine just a measurement device, but you don't really know what's inside. So you press a button, it gives you some answer. And Bob does the same. He also has access to some kind of device. He can ask questions to the device and receives some discrete answers. And what we require in these scenarios is that the events, basically like the pressing of buttons and the getting answers, these events are space-like separated. So there's no causal influence between the two events. And we also do not allow for communication between these two parties. So we really just imagine them being like trapped inside their labs, pushing the buttons and seeing the answers. So what the quantity that describes this experiment, like you imagine that there are many, many rounds of them pressing the buttons, seeing the answers. And what describes this experiment is what we usually call the correlation, which is simply just the probabilities of the outcomes. So what is the probability that Alice gets the answer A, Bob gets the answer B, given that they chose the settings X and Y? This is what we're interested in. This is what you have access to as the experimenter. You don't know what's inside your boxes, but you can collect these probabilities. And then once you collected these probabilities, you can just write them as like a real vector in like this high dimensional real vector space. It's kind of convenient to just collect this data in a long vector. So this is the scenario. And now we start putting models behind observed correlations. And the first one is the kind of classical model, which is called a local hidden variable model, which kind of collects our everyday intuition of how such a correlation might emerge. And what we have here is that we imagine that in every round, there is some kind of resource called lambda being distributed between the two parties. And then the parties, the way the parties obtain their answers, like Alice obtains A as a function of her setting X and this shared resource lambda. So this FA is just a deterministic function of X and lambda. So similarly for Bob, he has a different function, which is also a deterministic function of Y and lambda. And the correlation that we see is some sort of probabilistic mixture of such behaviors, because it might happen that in different rounds, a different resource is being distributed. So this essentially combines everything that we can imagine sort of in naively how such a correlation might emerge. And just notice that I put here deterministic functions, but this definition can also incorporate some probabilistic behaviors locally. So Bob's function does not have to be deterministic, but even if that's the case, the observed correlations can be written this way. So these are the kind of classical models. And now we move on to the quantum models, in which the shared resource is a quantum state on some tensor product Hilbert space. And the way to obtain information from the inputs and the state is via some measurements. So most generally, we will consider positive operator value measures, which are just quantum measurements. So Alice has a quantum measurement on her Hilbert space. Bob has a quantum measurement on his Hilbert space. And this is how, through the Born rule, they get access to these probabilities. And so if we start comparing these two models, we saw that in the local hidden variable model, which is now represented by this red square and an L for local, this is a probabilistic mixture of finitely many extremal points. So we get a polytope. And the quantum set, this is this green one, this is also a convex set, but this will be in general strictly larger than the local set. So we can get some correlations in quantum theory that do not have a local hidden variable model behind them. And the way, like one way to witness this sort of quantum behavior is through Bell inequalities. And these Bell inequalities are just some linear functionals of the observed correlations. So this is like an example. And the Bell inequality must be satisfied by every local model. So for example, in this case, in this drawing, like every local model should be on the top side of this hyperplane. So this is how one might experimentally confirm the inadequacy of local hidden variable models. And another intriguing feature of Bell non-locality, which will be kind of useful for us to understand device-independent quantum key distribution, is self-testing. So there are some results that tell us that in some cases, when we observe a quantum correlation, so let's say this point, just by seeing this correlation and not having to know anything about the state and the measurement, just the observation of a particular correlation in some cases implies that the underlying quantum state must be basically equal to some fixed ideal quantum state, this rho tilde, and also the measurements. So I don't write equality here because it's not an exact equality, but this means that the state that we use in the experiment must be equivalent up to some sort of trivial transformations to a specific fixed ideal state, and similarly for the measurements. This is just kind of a concept that's kind of useful in order to understand device-independent quantum key distribution, or DIQKD. So I will just tell you the kind of idea behind the DIQKD. So as you've already heard in the previous talk, the task of key distribution is basically for two parties. So again, we're still in this kind of two-party scenario. The task of these two parties to establish a secret key, which is this K, which you can imagine this is like a string of bits. So via some physical process, locally Alice and Bob want to create their key, and they want their keys to be equal, right? They want to share this key, but they also want these keys to be random, which means that to any potential third party, like an eavesdropper, this should be unpredictable. And the way to use, like an example to use quantum theory in order to achieve this task is, let's say we share a quantum state. I chose the single state of 2 qubits, and in this example, both Alice and Bob measure in the 0-1 basis, and you can see from here that whenever Alice gets the outcome 0, Bob will get 1, and whenever Alice gets 1, Bob will get 0. So after that, if Bob flips his outcome, they will exactly achieve this equality of their outcomes, and also they are random in the sense that there is an equal probability of getting, for example, for Alice, for getting the outcome 0 and for getting the outcome 1, and nobody can tell in advance what this will be. So this is the idea of quantum key distribution, and now we move to device-independent quantum key distribution, in which the protocol is kind of similar. Alice and Bob want to measure some quantum state and get some outcomes and build their key from the outcomes using some public communication. But they don't want to assume what the state is and what the measurements are. They only want to establish the secrecy of the key by looking at the observed correlations. And this is why self-testing is kind of like one way of thinking about how you can achieve this, because if you observe a correlation that, let's say, self-tests this singlet state and these measurements, then you can be sure that this state and these measurements are then useful for QKD. But you only want to infer this from the observed correlation, and you don't have to trust your devices, the measurement devices and the state source. This is why it's called device independent. And just one thing that is important to mention is that Bell non-locality is necessary for secure DI-QKD, because if you have a correlation that has a local hidden variable model, so it's Bell local, then you can always write the distribution like this. This is exactly the same equation that I had before. And you can imagine that this resource, this lambda, is being distributed by the eavesdropper, and the devices were constructed by the eavesdropper, which basically means that the eavesdropper knows the deterministic function fa and fb. And so essentially, the eavesdropper will always know the outcomes. This is because in standard DI-QKD protocols, this is what we call standard, eventually the inputs of Alice and Bob are announced in the public communication round. And once these are announced, the eavesdropper knows exactly the outcomes of Alice and Bob. And so the randomness is gone. The eavesdropper can be, in principle, completely correlated to the outputs of Alice and Bob. But what we show in our paper is that Bell non-locality is not sufficient for the security of these standard DI-QKD protocols. And the way we show that is we choose a specific eavesdropping attack, and we apply this attack to a large family of Bell non-local correlations. So just quickly, the eavesdropping attack, it basically consists of the eavesdropper manufacturing some measurement devices A and B, but the interesting part is that the eavesdropper distributes with some probability QL a local state, and with some probability 1 minus QL a non-local state. So the observed correlation by Alice and Bob will be described by a convex combination of a local and a non-local correlation. And this is kind of the core idea behind this attack. And it's kind of easy to analyze later using just classical cryptography tools once this attack is established. And we apply this attack to protocols which use the two-qubit Werner state, which is just a noisy version of this two-qubit singlet state. So this this orange state here, this is the Werner state with visibility V. So we think of like an imperfect realization of the two-qubit singlet state. And we allow for an arbitrary number of measurements, so X and Y can have values from arbitrarily large but finite, well, discrete alphabet, and they are projective measurements. And for these kind of correlations, it is known that if the visibility is at most this B local, this is roughly 0.6829, then every correlation that can be written like this is local. It has a local hidden variable model. And also it's known that if the visibility is at least this V non-local, then there exists some arrangement of projective measurement that gives rise to non-local correlations. These two results are in these two papers. And what we can show with our attack, okay, for the attack, we need to choose the local state and the non-local state. So for the local state, we can just use the Werner state with visibility V local, for which every correlation is local. And for the non-local state, we just choose the perfect singlet state. And using this attack on these protocols, we can actually show on this kind of same graph that up to this visibility, this V critical, which is larger than the non-local visibility, in this region, using standard DI-QKD protocols, Alice and Bob cannot establish a secure key. And this also means, because this critical visibility is larger than the non-local visibility, that there is this region here where you can observe non-local correlations, but it's impossible to extract a secure key using the standard QKD protocols. So this is a generic result, and maybe the most important implications to this is that all the commonly used QKD protocols. So these are the ones that maybe for those of you who know, these are based on like the CHSH inequality and some variants of it. All of these protocols become insecure while still being non-local. So if you go back to this kind of drawing, this is a slice of the set of correlations. And so this is a local set, but there's this little blue area outside of it where the correlation is not local, but you cannot extract the key if you observe these correlations using the standard tools. So these are the implications, and some of the limitations of further questions is that what happens if only one party announces their settings. So remember that in the standard protocols, we assume that both of the parties eventually announce their settings, the X and Y. But if only one party, there are a few protocols proposed in which only one of the parties announces their settings. And for these, we don't really know the answer yet. We don't really know whether non-locality is sufficient. And also, once we fix the state, there's also a question whether maybe we can improve the key rates using non-projective measurements. These are kind of the open questions. So thank you for your attention.
Thanks a lot, Máté. I really liked your clear presentation of these difficult concepts, very pedagogical. It was great at the beginning, and also the result is great. So let me start with a particular question which relates exactly to your figure there. So my question is that, like, for all of the Bell inequalities that you studied, you are claiming that that neither, for all of them, you had those cases where you could not have this key distribution protocol achieved, right? So this is your conjecture that there would be no inequality, like a hyperplane that would separate.
So we don't need to rely on inequalities. You only need to look at the correlation point, and you can say that if I observe this correlation, even though it's non-local, which you witness through a Bell inequality, but even though it's non-local, there is no way that you can extract the key from this correlation.
Okay, thanks a lot. So there is two quick questions. One is from Devdutt Sharma. Like, he asked whether your result is valid also for, do you think your result is also valid for multipartite Bell inequalities? Of course, you then also, of course, have to change the setting also.
Yes, this I don't really know. Yeah, I don't.
Yeah, although one would guess naively, yes, right? I mean, it would be a strange. I mean, one has to change the setting, of course, first of all, like the basic setting before one answers this question. Yeah. And then there is a question from Zoltán Guba. I'm going to read it. You said that there is a region for which a secure key cannot be extracted by standard QKD protocols. How do you define a standard QKD protocol?
So in the standard QKD protocol, what happens is that the parties, maybe this figure, there's a quantum state here, the parties measure, and in every round they obtain some outcomes. So they basically collect this correlation, the data for this correlation. Now the quantum part basically finishes, and then they reveal some part of their data in order to estimate this probability distribution, right? Because before that, they only have access to the marginal distribution. So they need to reveal some fraction of their data in order to estimate this. And once that's done, they also announce their input choice for each round. And this is like the most important assumption that we make. This is like the standard one, which is like almost all the protocols that have been proposed so far use this. So they announce the inputs, and then they end up with like some classical distribution that is shared between them. And from this, they try to extract the key using public communication. But from this point on, basically everything is classical. They have a shared distribution, P of AB, and using two-way communication, they are trying to establish a secret key. This is basically the standard QKD protocol.
Okay, thank you very much.